we need to design a special sort, heap sort, satisfying three requirements. Worst case in big theta of n log n, first requirement. Second, in place algorithms. That means the extra space used must be bounded by constant. Third requirement, it can manage dynamic data efficiently. Three requirements. To get a sort with these three properties, we rely on a special data structure, heap data structure. Heap, it is a near complete binary tree. But we want to store this heap, store our data in this heap data structure in a simple array data structure. Array. We don't want to use some very complicated data structure. To store a binary tree in an array, we need to do one special treatment. That is, we need to define parent-child relationship. So we have a simple way to define parent-child relationship. After that, then we need to add one special property to this heap data structure. We call it max heap property. Max heap. The values among three nodes, parent, two child nodes, and a parent node, these three nodes should satisfy certain inequality. Specifically, the value of the parent node must be greater or equal to the values of the two child nodes. Two child nodes are the most two child nodes. For some of the parent nodes, we may only have one child node, not two, only left child node. Here you can see this node. If it is a parent node, it only has left child node. It does not have right child node. All right, so that's the max heap property. After we have that, then we are ready for the heap sort. But to prepare for the heap sort, we need to prepare some supporting operations. Because when we work on the dynamic data, it is very easy that new added data may break the max heap property. So we need to fix it. If there is a possible violation in the heap, in the max heap, we need to fix it immediately. So this example shows the basic way we can apply to fix a violation that occurs at one specific node. Here I use the gray color to show the violation place. All right. So then we apply a special operation we call the local heapify operation. Local heapify. Yeah. In a previous slide, I gave you the pseudocode, how to work on a local triangle. Here, local triangle here. So we have detection part, Then after the detection, we swap the nodes to fix the violation problem. All right. And in this example, usually when we fix the violation problem, we need to follow this dirty node all the way down to the bottom level, leaf level. Yeah, let me call leaf level. Yeah, because if I call bottom level, it is very vague. What do you mean bottom, right? The meaning of bottom pretty vague. If we call this is bottom level, do we call this bottom level, right? Yeah, it's a little confusing. Yeah. But if I call leaf level, this leaf level, also leaf level, right? So no confusion. Yeah. All right. So now we are very close to the situation that we can apply the heap sort. But we need to do some more work. Yeah. Before the last step, we have some important step we need to do. So the next step is building a heap, this step. Because when we start from an arbitrary array, our given data is an arbitrary array. So definitely, in general, it does not follow the max heap property. No max heap property. So we don't have a heap object. We don't have it. So we need to work on our data to make it a heap. So this process, we call it build a heap. We need to, do some special operations on our given data to make it a max heap. Then we can start heap sort. Here, let me use a simple example. This is a random, arbitrary array. You cannot see any max heap property there. Random. So we start with this random array. Our goal is we want to change the locations of the elements so that we get a max heap object. Then we can do the heap sort. The question, how to do it? Yeah. The basic operation we need to use here is very simple. Local heapify. Yeah. Max local heapify operation. Local triangle, swap, the same operation we used before. Let's start. All right. First, we arrange. So we follow the natural order. Array has a natural order, right? Position 1, 2, 3. Yeah, because we ignore position 0. Yeah. Okay? Yeah. So position 1, 2, 3. It has a natural order. So position 1, we put at the root. Position 2, 3. So we fill a near complete binary tree with the given elements in the array following the natural order, and so on. Okay? Yeah. Just arrange them in that way. Yeah. Definitely, it's far away from a max heap. So our next round processing, we need to, I need to mute my phone. Yeah. I just missed the, this step. Yeah, in my preparation part, I missed this. Oh, something is wrong. Yeah. Let me put in the airplane mode. Yeah. All right. So now we need to, do the local Heapify operation on all the possible local triangles. Remember that max Heapify operation, we can only apply it on local triangle. All right. But when we apply it, so in this whole binary tree, Ray joined us. All right. In this whole binary tree, there are many different local triangles. So the question is, where should we start? Right? Where should we start? So we don't want to do the redundant work, right? Yeah. So we want to do our processing. Oh, sorry. Yeah, I saw some chat message. Yeah, okay. Yeah, don't worry. Yeah, yeah. We don't want to do redundant operations. That means when we do the local Heapify operation, we should follow some well-organized order. The order is important. So we need to follow some special order so that we do not miss any local triangle, but after we complete the processing, then we can get a max heap immediately. That's what we need to do. All right. So what is that order? Here, let me give you the order we will do for this step, building heap step. The order is bottom up. From bottom, then going up, level by level, going up, bottom up. So let's do the scan from the very bottom, and at the bottom level, we start from the right end, not left end, the right end. All right. The first local triangle we examine. So this is our first triangle. Okay. The bottom level, the right end. All right. We need to check violation, right? No violation. So this local triangle, no violation. Our local Heapify, our max local Heapify operation has that checking step. Yeah. So we just run that operation. Then we move to the next local triangle. Yeah? Because from right to left, when you're at the bottom level, so you move from right to left. The next one you detect. So there is a violation. So then you swap, remember, based on our, local Heapify operation, we swap these two nodes with value 2 and value 14 all the way down. Remember, all the way down to the leaf level to fix it. All right. After that, so we complete the bottom level part, right? Bottom up. So we need to move up, one level up. All right. So the next local triangle for processing, we detect another violation here. Then apply our local Heapify operation, another swap between these two nodes to fix it. All right, after that triangle, next one, from right to left, next local triangle. So we detect another violation. and we apply local heapify operation, swap between these two nodes. All the way down, remember, yeah, after swap, this node 1 moves to this location. It is still dirty. You need another swap until it reaches the leaf level. Then you stop. Yeah. So after that, yeah, that node 1 at a leaf level. All right. Then we move one level up. That's our last local triangle. It is also dirty, so we do another swap. But we need to follow this dirty node all the way down to the bottom level, right? Yeah, because you need to keep checking, following this dirty node until it becomes clean. Then you can stop. All right. After you finish all the local triangles in this order, bottom up, in each level from right to left, following the natural order, at the end, you will get a max heap object. Yeah. All right, so this is still, you need to move down, right? 4, yeah. At the end, that node located at a leaf level. Yeah. After you scanning, processing all the local triangles, you get a complete max heap object. So it's ready for heap sort. So this whole process, that's our building a heap process. Yeah? Okay? Yeah. So we can write a program to do operations. Yeah. But there is a question. Yeah. How much work do we need to do? Because later, after we complete the heap sort, we need to do the efficiency analysis, right? If this process is very slow, then it's not acceptable. If this building heap process, if we need to do comparisons, comparisons and the swap operations too many times. For example, if the number of operations we need, if it's big theta of n squared, definitely not acceptable, right? Too slow, too costly. Another one, if it is a little better, n log n, slightly better, but we know sorting the whole array, this is already the cost, sorting the whole array. So your preparation step, you need to take the same cost as the whole array sorting. So this is still not good. Yeah. So we want to get a faster, so the whole process, so we want it faster than these two asymptotic notations. Then we feel there is a chance we can use this algorithm. Otherwise, we need to look for some better one. Yeah. All right. So next step, we need to estimate the total cost of this process. building a heap process. Yeah. All right. 8.5, heap nodes in each level. In order to estimate the cost, we need to really study the heap nodes in all the levels in the heap. That information is very important to estimate the total cost. All right. So let's start from the bottom level, bottom up. So we start from the bottom. Number of leaves in a heap. Given a heap, can we find the number of leaves in this heap? We need to find a formula for the number of leaves. That's pretty easy. So let's look at this question. First, how to describe leaves? We need some formula to describe leaves. Given an array, if you know the array size, the number of nodes in this array, then if we also have the index number, the location, position number for one particular element, the question, can we find if this node is a leaf node or not? First, we need to answer this question. How do we know a given node is a leaf or not? So let's do some analysis here. Here, we need a heap example. All right. First, we need to identify those leaf nodes. Oh, because here we talk about leaves. I think you have some basic knowledge about trees, right? In your discrete math. So you study some basic background knowledge about trees. Leaves means those nodes without children, without any child. Yeah. Leaf nodes. So other than leaf nodes, so here in this figure, we have 5 leaf nodes. Other than the leaf nodes, the remaining nodes, they are not leaf nodes. Yeah. So other than leaf nodes, we call internal nodes. Internal nodes. Leaf nodes, some people also call it external nodes. All right. Same thing. Yeah. Internal, external. All right. Now we need to find some inequality to describe all the leaf nodes based on their indices. What inequalities should we use to represent all the leaves in the heap? Yeah. We need to examine parent-child relationship. Yeah. If the parent, its index is I, then it's left child. Here we look at the left child, not right child. Right child, sometimes a parent node may not have right child. If an internal node, it always has a left child node. So based on that certainty, we select left child. Left child, A of 2i. The question, because our goal, we want to describe leaf node. If we look at the leaf node can never be a parent node, right? A leaf node can never be a parent node. That's the description, property, basic property for a leaf node. A leaf node can never be a parent node. That means if you look at its possible left child node, you double the index 2i, this 2i index will be out of the bound, right? Out of the range for the array indices. That's the way we describe leaves. Out of the range. Out of the range. When you double it. If it's in the range, then you get a valid parent node, right? Yeah. A leaf node cannot be a valid parent node. So based on that analysis, we can write out the inequality describing all the leaf nodes. Yeah. 2i, we'll double it. This I, we'll double it, 2i. 2i must be out of the range. What is the range? What is the range for valid indices in a heap? From 1 through n, right? Yeah. Lower bound is 1. Upper bound is n, between 1 and n. Yeah. All right. So meaning of no child, this property, and I, first, the index I must be in the range, right? I less than or equal to n. This leaf node, its index I must be within the range. So that's the first inequality. Second inequality, we double it, it is strictly greater than n, that means it is out of the range. That's the condition. Okay. All right. Now let us work on this inequality. We want to describe the range for the I index. What is the suitable range for this index I? Index range in this interval. Yeah. All right. So then we do division by 2, n over 2 less than, strictly less than I. So we need smallest integer that is strictly greater than n over 2. How to describe it? Strictly greater than n over 2. Cannot be equal. Here we do not allow equal case. Strictly greater than n over 2. How to represent it? We need an appropriate formula to represent it. That is floor function of n over 2 plus 1. Floor function. Floor function we know less than or equal to this n over 2. Yeah. Based on n is even or odd. When n is even, they are the same. They are the same because strictly greater than this number, so we need a plus 1. All right. When n is odd, n over 2 floor function is smaller than this n over 2, but after we plus 1, it is greater, strictly greater than n over 2. Yeah. So this is the appropriate expression for the lower bound of I. So we get a lower bound. Upper bound, it's already there, right? I less than or equal to n. So we find appropriate range for index I. That is this inequality, both with equalities included. All right. So the next question. We want to count number of leaves, right? So the question, how many index I numbers can we find in this range? Simple counting question. We want to count the number of integers in this range. The answer, very simple. The answer is n minus what? Minus n over 2 floor function. No plus 1. Because this number should be included. So actually we use the upper bound to minus this lower bound, the number that is right before this lower bound. It's not the upper bound minus lower bound. If you use upper bound minus lower bound, then this lower bound number is not included because you take it away. After the subtraction, you take it away. We don't want to take it away. We want to include it. So that's why you minus the number right before this lower bound. Then you do not exclude any integer in this range. So this is the formula, n minus floor function of n over 2, the number of leaves. All right. Yeah. But there is another equivalent formula. So this n minus floor function of n over 2 equals ceiling function of n over 2. Yeah. Ceiling function of n over 2. Yeah. So these two formulas, they have the same values but in different forms. Yeah. Sometimes the first formula may be better for our current situation. Sometimes the second formula is more friendly for our current situation. Yeah. So we have two options. Yeah. All right. But the question, how to see they are the same, right? Yeah. So here, I say they are the same. How to see they are the same? You can prove it easily. How to prove it? You need to consider two cases. When n is even, you can remove the floor functions, ceiling function sign easily, right? You see they are the same. When n is odd, you know how to remove the floor function and the ceiling function, and you can show both sides are the same value. So you can prove it. Yeah. And in our textbook appendix, this page, this formula is given. Yeah. All right, so here, we use this formula. All right. So we complete the first step. Count the number of leaves. That's the first step. After that, then we need to move up, level by level, bottom up. We need to go through all the levels in order to estimate the building cost. We need to look at the total cost for nodes in all levels. We need to do, if we recall our building process, we apply the bottom-up local heapify operations, level by level in certain order. We go through all the possible local triangles. So for that reason, we need to calculate how many local triangle processing we have done. So next step, number of internal nodes with height 1. So we move one level up, height 1. So here, let me recall or clarify the concept height. Because this concept, for many students, it's very confusing. What's the meaning of height? Here in this place, in our context, Heapsort, this context, the meaning of height. In other places, the height could be different, right? Yeah. Sometimes, it could happen. The same concept, same name, at different places. The meaning could be slightly different. Yeah. Here, let me draw a simple binary tree. Yeah. Like this. All right. Height. When we talk about height of each node, right? So when we talk about height of what? Height of one node, right? Yeah. Height of one node. Yeah. How do we need to do the counting? Level counting, number of levels. All right. The definition of height is, all right, we start from this node. Then we move down to one of the leaves. You have many leaves, right? Yeah. So you can find many paths from the current node to one of the leaf node. One leaf. But you select the longest path. Okay? Yeah. This is the longest path. You do not select this path. This is not the longest path. So you select the longest path. After you get the longest path, you count the number of edges. Number of edges. Edge 1, edge 2. So you have 2 edges in this longest path. Then that's the height. So your height is 2. All right. And many students, they count from top. They count this height. That's wrong. All right. Many students, they didn't watch the video, so when I give them questions, they just use their intuition to do the understanding. So height, you said height, then they use this mean. No, so that's not our definition. Our definition is this one. That's the height, the meaning of height. That one, another depth. Yeah. So we use a different name, different concept. Yeah. Here we only use this height, meaning. Yeah. Height 1. Yeah. Height 1. This node, edge, only one edge, the path. Height 1, right? Height 1, right? Yeah. But not this one, okay? Not this one, because although one edge, but it's not the longest path. Okay. So based on this understanding, now we want to count the number of internal nodes with height 1. After we find the formula, then we want to generalize to height h. After we get height 1, we have some better understanding, so we can extend our formula for the general case. easily. All right. Now let's look at the height 1 case. Based on our understanding, in this simple example, there are these 3 nodes of height 1. The question for a general heap, how do we find a formula of height 1? Here we can use the similar method we used to calculate the number of leaves. We need to extend that formula a little bit. But the thinking pretty much the same. Let's look at the number of all internal nodes. How to find the number of all internal nodes? With height greater than 0. Leaf nodes, these leaf nodes, we call height equals 0. For all the leaf nodes, the height equals 0. Internal nodes, all the internal nodes have positive height greater than 0. Their height numbers are greater than 0. So now we want to count the number of all internal nodes. Okay, yeah. All right. Total nodes n. In a given heap, we know for each node there are only 2 types, right? Leaf node or internal node. Only these 2 types. And they are mutually exclusive. All right. Based on this understanding, we know the number of leaves. Then the complementary part will be the internal part, right? Yeah. Number of leaves, we get that formula. N minus floor of n over 2. That's the number of leaves. Complementary, n minus this number. So the number of internal nodes equals floor of n over 2. That's simple. But this is the number for all the internal nodes. The internal nodes with all the possible positive heights. This number. All right. Next, we only want to count the number of internal nodes with height 1. Right. How to describe it? We need to look at the local triangle. Its parent node has height 1. And we look at their leaves. Left child node. Children, yeah. So the description. How do you describe internal nodes with height 1? Yeah. One quick description is their children must be leaves, right? Yeah. Because you go down 1 by 1 level. When you move down 1 level, you reach the leaf level. So you look at the left child. It's left child. Yeah, because it's right child, it may not have the right child, right? So you look at its left child node. It must have a left child node. So you look at the index of its left child, and you know its left child node must be a leaf node. And you know how to describe leaf node, right? So you use the leaf node formula to describe the left child node of an internal node with height 1. So that's that idea, right? 2i, that is left child, right? Yeah, left child. So you look at the index of its left child, 2i. 2i must be a leaf node, and it must fall into this range. Yeah. So that's our new description. All right. Then let us calculate the range for index I, because our final description must be on I, not 2i, right? I for the parent node, not child node. So we need to look at the range for I. So we do division by 2. Division by 2, upper bound, relatively easy, right? N over 2. But the upper bound should be an integer, right? So we take floor function, round it down. If n over 2 is non-integer, then we have room to improve slightly on its upper bound, so we round it down. So you can understand we need to apply ceiling function. Sorry, a floor function. Floor function. Yeah. Sometimes I pick the wrong one. Yeah. Floor ceiling. I pick the wrong one. Yeah. All right. And the lower part. Yeah. 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 Floor function. Remember +1. +1 we move up, right? Yeah. Yeah. So the divided by 2, it's a non-integer expression, but we need to round it up, right? Not to round it down. For the lower bound, we round it up. Yeah. But then we simplify the formula, get this one. Yeah. Here, I use this formula, okay? All right. Ceiling function, look at it here. Yeah. The first step, we should use the ceiling function because we want to round it up. Lower bound, we want to round it up to get the best lower bound. All right, and division by 2. All right. But this rounded up, we can simplify the math formula to get this one. Floor of n over 4 plus 1. How to see that? So you may ask me how to see that. So this time, this formula is a little harder than the previous one. The previous one, when you look at it, even odd, 2 cases, you can prove it easily. But this one, we can still prove it. But when you prove it this time, you need to consider all the possible cases. So you need to consider total 4 cases. Because the denominator is 4, that means for n, you need to consider 4 cases. Yeah. So these 4 cases, n mod 4. You look at the remainder. N mod 4, remainder 0, remainder 1, remainder 2, and the remainder 3. So there are 4 different remainders when you do modular operation on n to 4. Yeah. These for each case, you need to verify. Case 1, verify. Case 1, you can make n equals 4k. Case 2, you can use n equals 4k plus 1. And so on. Plus 2, plus 3. 4 cases. Plug in. Yeah. Left-hand side, right-hand side. Then you compare both sides for the verification. Yeah. So you can verify it. Yeah. After that, you know this formula is correct. So we can use the simplified formula here. Upper bound, lower bound. All right. Then we need to do our last step because our goal is counting, right? Counting the number of internal nodes with height 1. So we use the same way. Upper bound minus, not lower bound directly, the number right before the lower bound. That's the way we do the counting. Our counting formula is this. Number of internal nodes with height 1. Upper bound, floor of n/2, minus the number right before this lower bound. So that's this number. Yeah. So that's the final formula. But this final formula, remember, sometimes we may like to use a different form, more friendly form in certain situations. Here, the situation, later, because remember we estimate the building cost, right? Our target, we want to estimate the building cost. For that purpose, we need to use this more friendly formula. But this one, it's not equality, it's inequality. Less than or equal to this one. So different from the leaf case. Leaf case is the equal case. For the internal nodes, here we need to use the inequality. How to see it? Yeah, people may ask, how do you know equality or inequality? Very simple. You use these 4 cases, 4 different remainders. You verify. For some remainders, you get an equal case. For some remainders, you get an inequality case. That overall inequality. Yeah. All right, so we complete our second formula. Next, we are ready for the general formula. Any height this time. Height h. H. General formula. Our last formula for estimation of the building cost. Generalize the previous result. All right, so let's do a summary. Number of leaves n minus floor of n/2. Now a height 0 corresponds to height number 0. Number of internal nodes with height 1. The range, this is the range. The counting number, this is the counting number. All right. Yeah. But remember, height 1. Okay, height 1. Now, we need to following, here you can observe some rule. So we want to generalize the rule. Number of nodes with height h. The range 2 to the h plus 1. 2 to the h plus 1. 1 plus 1, 2. Upper bound 2 to the h. 2 to the first. Induction, right? So here we use, induction way. Yeah. All right. Then the counting number of nodes, internal nodes with height h. Yeah. Generalize that counting formula. Yeah. Height number plus 1. Subtraction between these 2 floor function expressions. Okay. All right? Yeah. If you like, we can verify it. We can use mathematical induction to verify it. Yeah. You can treat this as a guess. Yeah. Because when people use the induction way, it may not be reliable. sometimes you may get it wrong. In order to confirm your guess is correct one, we can apply mathematical induction to prove it. Here we can prove it. Yeah. But I skipped that part. It's very easy. Yeah. Similar to the way we find the formula for the number of internals with height 1. Similar to that. Yeah. All right. This is our final formula. Now we are ready to do the estimate. Yeah. All right. Yeah. 8.6, building cost of a heap. Now we are ready to estimate the building cost. Right. Combine the cost of all heights. Because we go through all the local triangles for the internal nodes of all heights, right? Yeah. Leaf nodes, no violation, right? So when we run the building process, we go through all the internal nodes. We do not need to do any processing on the leaf nodes. Because regarding the leaf nodes, there is no violation of the max heap property. All right. Now, so let's look at the leaf nodes, or all the nodes of height h. Starting from 1, and the largest the height, look at the largest the height of the root node, largest the height. All right. Here, there is this one. This is the estimate. Remember, I said friendly expression when we count the number of internal nodes of height h. Number of internal nodes of height h. There is the exact formula, the subtraction one, but that one is not convenient to use. So we like to select a different one, slightly greater than that exact formula. So this one. Yeah, because it has only one term. Yeah, the reason it has one term. That exact formula has two terms. Not very convenient. One term here. All right. Then, what's this? So now, this part, we need to look at the diagram a little bit. Another general heap case. All right. Height A, we need to pick typical heap, typical internal node with height h. Here, this one. All right. To fix the violation that occurs at this node. Now, we assume there is a violation here. So we need to run that max local heapify operation to fix it. All right. And remember, number of edges is height, right? So when you run max local heapify operation on one local triangle, you move down one level, right? So you have total h edges, so you need to go at the most h steps. H steps. right? All right. Each local triangle, your cost is bigger of 1, right? Then you go h steps, so your cost is bigger of h. Yeah. Each node, you need to, when you fix the violation, you need to pay this much cost. That is the cost you need to pay, you need to cover. Okay? But you have at the most this many internal nodes of this height. Then the multiplication. The cost in height h level, height h, this level, that's the total cost. All right. Next, we need to accumulate total cost of all the positive heights. All right. From 1 to floor of log base n. Floor, yeah. It looks like ceiling, right? Yeah. 1, 2. Yeah. Oh, floor, not ceiling. All right. Yeah. How do we see floor or ceiling? Yeah, here. So, yeah, because here, some people may wonder, how do you know floor function or ceiling function? Yeah. So let's look at a simple example. All right. Another special case to give you some idea, to give us. Here there are 7 nodes, right? N equals 7. Yeah. And we need to consider height 2, right? Yeah. The root node has height 2 based on our height definition. That is the log base 2 of 7 floor function, right? Not ceiling function. Because ceiling function you get 3. So not a ceiling function. Yeah. So from that simple experiment, floor function is correct from 0 to this expression. Next, we write the summation formula because we need to accumulate the cost of all those levels. All right. Yeah, because for leaves, no cost, right? No building cost for the leaves. So we do not look at the leaves. All right. Summation h from 1 through the largest possible h. Then for each level, the formula, right? Yeah. So greater or equal, yeah, we know the total cost greater or equal, ceiling function, then multiply that big O of h. So we need to estimate this building cost. If you can complete this summation step, then we complete the building cost estimate step. So we know after that we will see if this method is acceptable or not. If the cost is too high, then this method is not acceptable. We should reject it. We should find a better one. If the building cost is not very high, yeah, in an acceptable range, then we can consider the solution. All right, so let's do the summation math calculation. This ceiling function is not easy to work. Yeah, because sometimes you need to round it up. Sometimes you don't need to round it up, right? Yeah, so that's, not very easy to work on. So the better, here, we are more generous. We enlarge the value of this expression by the inside the ceiling function, the fraction inside the ceiling function plus 1. It's larger than that ceiling function. So we estimate, so we enlarge the expression slightly for each term. Then we calculate this summation. No ceiling function, it should be much easier. So let's calculate our new summation. 2 terms, inside parentheses, 2 terms. Let us separate these two terms. First summation and a second summation. Second summation, much easier. Much easier. Okay? Yeah. So we estimate second summation first. All right. This big O thing, people can consider C constant or C1 times H. Yeah. All right. So we can take it out. Okay. All right. Not take it out. Take the C1 out. Take C1. That's C1 out. All right. Inside consecutive integers, right? Yeah. Inside consecutive integer 1 plus 2 plus log base 2 of n. So we have our summation formula. Yeah. So you can see this is big of log n squared. The second summation is this small, this large. Yeah. Very easy to estimate. So our major part of the original summation is first summation. That's the major part. Yeah. So let's estimate our major summation, main term. Yeah. All right. Another C, yeah, because this big O, can consider another constant C multiply the part inside. Yeah. Yeah. So we can, because in this summation, n is treated as a constant. During this summation, we never change n, right? Yeah. Each value changes from 1 through floor of log of n. N is treated as a variable. H is treated as a variable. N is treated as a constant. So we can factor out the constant n. Inside, we need to take summation h variable over denominator power of 2 to the h plus 1. So now, we want to see how large is the part inside the summation, and the whole summation, how large we can get. All right. Then we do another enlargement, more generous, because the upper bound, the upper limit of the summation, it is a log function. Log function is very hard to work on, right? Yeah, very hard to work on, log function. Yeah. So now, we need to be more generous here. Again, we enlarge the upper limit to infinity, how large it is, how generous we are, right? Yeah. Infinity. That means we add more terms. Even that, yeah, because for the later terms, all the fractions are very small. So we're willing to add more terms to see what is the total summation. All right. So next, we need to now, after many rounds of simplification, because if the upper limit is the infinity, it is much easier to calculate, right? Yeah. So next, we calculate this simplified summation. All right. Let us take a break after you come back at 7 o'clock. So we calculate the summation. So then after that, we are ready to do the quick sort. Not quick sort, heap sort. All right. Yeah.